In this example, the diagram shows a particle in equilibrium. Notice here with this force that we don't know the magnitude t, and we also don't know the angle that it's projected at. We've previously seen an example like this where we ended up using simultaneous equations to solve. So we'll start by resolving perpendicular to the slope. We've got the 6 Newton force acting straight out of the slope. We have a component of force t. We're not crossing the angle, so that will be t sine alpha. Acting into the slope, we have a component of the weight force. This angle in here is the same as at the foot of the slope, 30 degrees. As we're crossing the angle, we get 8g cos 30. And as everything is in equilibrium, this equals 0. We'll rearrange to make t sine alpha the subject. And we'll label this equation 1. Next, we'll resolve parallel to the slope. We'll take upwards to be the positive direction, so we have a component of force t. We're crossing the angle, so that will be t cos alpha. We have the 14 Newton force acting in the opposite direction. We also have a weight component acting down the slope. As we're not crossing the angle, that will be 8g sine 30. It's in equilibrium, so that equals 0. We'll rearrange to make t cos alpha the subject. And we'll call that equation 2. Now, since we have t sine alpha in one equation and t cos alpha in the other equation, we'll divide equation 1 by equation 2. T divided by t cancels. Sine alpha over cos alpha gives tan alpha. And on the right hand side, 8g cos 30 minus 6 divided by 8g sine 30 plus 14. Putting that into our calculator gives tan alpha equals 1.16 and so on. And if we do inverse tan, we get alpha equals 49.3 to 3 significant figures. To find t, we'll substitute back into equation 1. So dividing through by sine alpha gives us t equals 8g cos 30 minus 6 divided by sine 49.3. Remember to use the exact value here, and if we put that into our calculator, we get 81.7 newtons to 3 significant figures. Okay, here's one for you to have a go at. Pause the video, then come back and check your solution against mine. Welcome back, here's my solution. So we've got a diagram where a particle is in equilibrium, and we need to find p and theta where they're both involving the same force. So we'll start by resolving perpendicular to the slope. We've got 80 newtons coming out of the slope. We've got a component of p acting out of the slope. We're not crossing the angle, so that will be p sine theta. We've got a component of the weight going into the slope. The angle here is 60 degrees, which is the same as at the foot of the slope. So we get minus 30g cos 60. It's in equilibrium, so that equals 0. We'll rearrange to make p sine theta the subject. And we'll call that equation 1. Next, we'll resolve parallel to the slope. Let's take upwards as positive. We've got 400 newtons to start with. In the opposite direction, we've got a component of p. We're crossing the angle, so that will be p cos theta. We also have a component of the weight force down the slope. We're not crossing the angle, so that will be minus 30g sine 60. If we rearrange this to make p cos theta the subject, we get p cos theta equals 400 minus 30g sine 60. We'll call that equation 2, and then we'll divide equation 1 by equation 2. P sine theta divided by P cos theta gives us tan theta, which equals 30g cos 60 minus 80 over 400 minus 30g sine 60. And if we put that into our calculator, we get tan theta equals 0.46 and so on. And then if we do inverse tan, we get theta equals 25 degrees to two significant figures. Recall that we're using g as 9.8 here, so that's why we get 2 sig fig here. Next, we'll sub back into equation 1. Dividing through by sine theta gives us P equals 30g cos 60 degrees minus 80 over sine 25. Remember to use the exact value for sine 25. If we sub that in, we get 160 newtons to two significant figures.